Because the previous problems were too easy, we're going to change this up a bit and we're going to revolve a region around an axis other than the x-axis. So in this case, we're going to take this region and revolve it around the line y equals -2. So I have here the curve y equals tan x plus 1 and y equals 1/2 x. And by the way, just to be clear, y equals tan x plus 1 means y equals tan x plus 1. It does not equal tan of x plus 1. I'm going to erase those. So just to be clear what we mean. Okay, so what we're doing, and I'm not even going to attempt to draw this to scale, since this line down here is now the axis of revolution, what we're doing is we're revolving both curves around that axis, giving us sort of an inner circle. It looks like this. I'm not even attempting to draw the center of the circle where it really is, because I'm just going to run out of paper if I do. And the outer circle will look like this. So once again, I do have a washer. And if you think about what the radius is here, the radius, the inner radius, is just going to be the distance from this point. So that point is x comma 1/2 x. If I just used 1/2 x, I would only get the distance from that point to the x-axis. So I need to actually go further than that. So this is going to be, so I can really just subtract top minus bottom to get the distance, just like we did with area. So the radius is going to be 1/2 x minus -2, which gives us 1/2 x plus 2. And then I can do the same thing with the outer circle. So the outer circle, getting the vertical distance between this point, which is x tan x plus 1, I can get that the outer radius is just going to be tan x plus 1, and then I need to subtract -2 again, so that gives me tan x plus 3. So there are my two expressions for the inner and outer radius. I'm now ready to form the integral. Recall that the volume of a solid of revolution is equal to the integral on the interval. So let's define what the interval is. And I put these in just because I partly because it's a trig function, but because I want to get you used to using numbers that are more complicated than just integers. I'm going to put in the lower limits, pi over 6, the upper limit, pi over 4, and now I just have pi times the outer radius squared minus the inner radius squared. So the outer radius squared is tan x plus 3, and I have to square that. And then the inner radius is 1/2 x plus 2 squared. The inner radius is 1/2 x plus 2, and then I have to square that, giving me the squared. And then finally I put dx. And by the way, I'm leaving the pi inside here, but you'll often see the pi written outside the integral when you know it's a volume of revolution by the washer method. That's the most common way to write that, and you'll see that in the book. I may ask you to recognize it in both ways. But one thing you do want to recognize is that this expression is the area, this including the pi, and that's one reason to write it inside if you want, the area of one washer cross section. And of course, if I multiply it by dx, that gives me the volume of one washer-shaped slab. So, okay, this is an example where there's a different axis of revolution where it's not the x-axis, and that axis is below the region. Okay, so now we're going to change it up again a little bit and find the volume of the solid formed by taking that same region but revolving it around a different axis. And I want you to see what changes here. In this case, I've chosen the axis y equals 7. I've chosen a 7 just because it's high up enough that you should be able to recognize it lies entirely above the region. You should know enough about trig functions to realize that this function y equals, let me just write it in here, y equals tan x plus 1, write it a little neater. And this function here, of course, is y equals 1/2 x. You should be able to recognize that this point at pi over 4, the tangent of pi over 4 is 1, so if I add 1 to that, I get 2. So this is the point pi over 4 comma 2. So the highest point in this region doesn't come anywhere near the line y equals 7. We can rest assured the entire line is that the entire region is below the line y equals 7. And by the way, I'm not going to give you an axis that runs right through the middle of a region. So here's what's different about this. if you look at what happens when I revolve around the line y equals 7, I'm going to get, for a typical circle, I'm going to get this is the inner radius, and this is the outer radius. Now, recall the previous example. The green line was forming the inner radius, and the purple curve was forming the outer radius. When I put the axis above these regions, that's going to switch, which means that now this inner radius, let me do it in the other color, this inner radius here, right, lowercase r, is equal to, is going to be equal, I'm going to take top minus bottom. So the top of that in order to get the vertical distance. So now the high point comes from the line y equals 7, and it's the low point that comes from the curve. So I'm going to take 7 minus parentheses tan x plus 1. So that equals 6 minus tan x. So see how we do that? We now take the axis and subtract the function instead of taking the function and subtracting the axis. And I can do it here. For the blue line, this is going to be, outer radius is going to be 7 minus 1/2 x. So a couple of things change. Number one, when finding the vertical distance, when the axis is above the region, in order to find the vertical distance, I have to subtract the axis minus the equation for the curve instead of the equation for the curve minus the axis. The other thing that's going to change is that now it's the top curve that forms the inner radius and the bottom curve that forms the outer radius. Go back to this example earlier, what you can see is that it was the bottom curve that formed the inner radius and the top curve that formed the outer radius. So a couple of things switch when you put the axis above the region. So now we can write out the integral. In fact, I'm going to do it the way I said. We're going to write the pi outside and then just do outer radius squared minus inner radius squared. We're going to put in the same limits of integration, pi over 6 to pi over 4, and now we're going to do the outer radius is 7 minus 1/2 x. We square that. And the inner radius is 6 minus tan x, and we square that. And dx, and that gives us the integral.